All right, 16 says that we have to do BA minus 3 CD. So we'll start by computing BA and CD. So for BA, I can tell that B is the tail and A is the head. So if I do head minus tail, yes. So if I look at the picture, the B is underneath the tail of the arrow, and the A is underneath the head of the arrow. Cool? Great. For CD, again, C is the tail, and D is the head. So if we do head minus tail, we got that. So if I say BA minus 3 CD, that's going to be negative 2.5 minus 3 times 1 negative 3. And I'm probably going to think about this instead of minus. I'm going to think about it as like plus a negative. So I'll do that scalar multiplication first because that's the first thing we do in order of operations is multiply. And then if we add these then, got that. So that's the component form. And then if I want the magnitude, that's the square root of negative 5 squared plus 14 squared. Or the square root of the x component squared plus the y component squared. So that's 25 plus 196, which is 221, I think. And I don't know if that's a perfect square or not. It looks suspiciously like one to me, but maybe it's not. Nope. Well, I guess I should have known better because 14's right there, and then 225 is 15 squared. I just double check that I did that arithmetic right. It's early in the morning, and you know you never can be too careful. No, that's right. And I don't think that'll simplify anymore. That radical 221. It's not divisible by 3. I don't know. Is it an 11? It looks 11-ish. Nope. It's not 2, it's not 3, it's not 4, it's not 5, it's not 6. It's no, it can't be 7 because it ends in, there's nothing, 200 isn't divisible by 7 because 21 and not 8. I don't think that's a 9. No, it can't be a 9 because it's not divisible by 3. I don't know. I don't think it might be prime for all I know. Or if it is, it's going to be like 17 times 19 or something like yuckarooskies like that. 17 times 13. There you go. That's what it is. But that doesn't simplify the radical anymore, so it's just that or the decimal. Does that feel okay, Eve? Yeah. Okay. Tia, did I see your hand raised for questions earlier? When I was asking if people had things, I thought I saw somebody in the back, but I might have just been like seeing heads or something. Oh, okay. Do you want to ask something? Okay. 22? Sure. So it says find the unit vector in the same direction as the vector indicated below, and then write your answer in component form as well as a linear combination form. So reminder that my formula for doing this is going to be 1 over the magnitude of my vector times the vector. Right, that's my unit vector in the same direction. So if I start by doing that, so fill in our numbers. 6 squared is 36, 11 squared is 121, so that's 150 square root of 157. I don't know that that radical is gonna reduce at all. So I'll do the scalar multiplication through. So far, so good, Tia. And then probably we rationalize those denominators. I'm not positive if 157 like simplifies at all, but it's not divisible by anything like nice, right? Not divisible by 1, 2, 3, 4, 5, 6, 7, 8, or 9. Yeah, I didn't do 11 or 13. It won't be 15. I guess it could be 17. That seems unlikely. No. Maybe 19? Yeah, I don't know. It's not going to simplify any. But we'll rationalize those denominators. So that's like my component form, where I just rationalize the denominator there, Tia. Now, linear combination form, what does that mean? That means it has the i's and j's in it, the unit vectors. So this is really easy. Just the x component is going to be my scalar times the unit vector I. And I'm going to have the y component times the unit vector j. So I is just gets tacked onto the x component, and j just gets tacked onto the y component. And that's my unit vector, or my linear combination form of the same vector. Yeah, Colby. That's I. That's the vector I with the vector hat on it. So this is our linear combination form. So the linear combination form, like for component form vector AB, that's AI plus BJ. I is always the x vector, and j is always the y vector. Because the vector I is the vector 1, 0, and the vector j is the vector 0, 1. So if I do the scalar multiplication, add those together, I'm going to end up back at AB, right? Does that feel okay, Cole?
Yeah.
T, are you happy? Okay. Josh.
19 is going to be a hard time remembering that.
Okay. Yep. So that's the same set of problems here. So again, I'm going to do 1 over the magnitude of u times u. The u in this problem is -2, -7. Two squared is 4, 7 squared is 49. The square root of that, so that gives you 1 over the square root of 53. Now I know that doesn't simplify. I do the scalar multiplication through. That's negative 2 over the square root of 53 and negative 7 over the square root of 53. And then we'll rationalize those denominators. So that's my component form answer. Okay with that so far, Josh?
So, yeah.
And then to get the linear combination form, all we do is take the x component, we put the vector I attached to it, and then we take the y component and attach the vector j to it.
So it's like linear.
That's the linear combination form,
The first one is the
component form.
okay.
So again, like part of the hard part about this is just getting all the names and the vocabulary under, you know.
Much like, you said, like, if you simplify that first part, the 1 over -2 squared 2, if you just, that part there.
That's
so
just,
if you just solve that, then you can solve the rest.
yep.
Alright, so.
Yep. So just basically plugging into a formula and grinding through to the end. And then just rearranging some stuff, but it should be pretty okay. Colbs. 40, sure. So 40 asks to show that two vectors are orthogonal to one another. Oops, that wasn't where that was supposed to land. Sometimes OneNote gets its own ideas here. So if you remember in the notes last time, we said two vectors are orthogonal if and only if their dot product is 0. That's what I'm going to be using to check this. So I'm just going to check by doing u dot v. And checking to see what I get there. So when I do that, I get to do the dot product, we do the product of the x components plus the product of the y components. 8 times -3 is -24. -1/2 times -48 is +24. Those add to give us 0. So I can say that u and v are orthogonal. Yes?
Split the second part and the first part. Like,
So I multiply the x's together,
yeah. Oh, okay, yeah.
and then we multiply the y's together,
Okay.
and then we add up the result. Aaron? Yep. Colbs, you happy there though?
Yeah.
Okay. All right. 28. This is asking us to prove the following dot product property. This will be the last one we do before we start the new stuff. We can do more questions next time if there are more. So I'm going to say, okay, I'm going to let u, the vector u, I'm going to define as the component form vector u1 comma u2. So if I do that dot product, that's going to be like u1 u2 dot u1 u2. So the definition of a dot product says I multiply the x components together and then I add them to the product of the y components. When I multiply u1 times u1, I get just u1 squared. I multiply u2 times u2, I get u2 squared. And this I know is the same thing as if I take this and square root it and then square it right afterwards. Right? That's like doing nothing at all. If I square root something and then square it again. And the reason I'm doing that is because I recognize that this is just the formula for the magnitude of u. And I'm done now. Because I've shown that. Oh, come on now. That is equal to that. Does that feel okay? And all of those proofs kind of work the same way. I'm just going to define things in terms of like in a component form, like I did there with my u, and then do my vector operations and use the definition to kind of pull out the piece that I need at the end. I wouldn't ask you to do anything like that on quiz or test. Just as an aside. All right, so today we're going to be talking about some application problems for vectors. So we're going to talk about two major applications. The first application, we already have all the tools we need in order to do that. The second application, I'm going to have to define a new vector operation before we get to it. So a very common example of a vector application is one of these navigation problems. So it says a boat leaves a port and averages 40 knots, that's nautical miles per hour, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? Before we do this, there's a word in here that needs a definition because we've never used this word before in regard to an angle. So that's a course or a bearing. When we're talking about navigation, we define direction a little bit differently than we do for like a standard position angle. So for courses and bearings, we're always going to kind of think about the compass rose. We always start at the north, and we're always going to rotate clockwise. So for example, if I take 215 degrees, I start at the north, that's 90, 180, and then like 35 more. Is everybody okay with how I drew that bearing? Now, the catch is that I don't want bearings in my problem. I want standard position angles so I can just use sine, cosine, tangent all willy-nilly and not have to think about it and make any adjustments. So the first thing I'm going to want to do is come up with a way to translate that bearing into a standard position angle. So for a standard position angle, we know we start on the positive x-axis and go counterclockwise. So that's 90, and the second quadrant's 90. And then how much left do I have in the third quadrant? 55. 90 minus 35. So my standard position angle then should be 90 plus 90 plus 55, so 235.
Why do we start at east?
because when we draw a standard position angle, it always starts at the positive x-axis and rotates counterclockwise. Right? That's the rule from first semester about standard position angles.
Yeah, I just got freaked out. It's forced.
Yep. So I'm just talking about converting now in between the two. Does that feel good to you guys? Okay. All right. So I'm just going to kind of like separate that off as like a little separate thing. So when I read this problem and the boat leaves the port, it goes at some speed in some direction, then changes direction, changes speed. First thing I'm going to want to do is take that information and convert it into like a magnitude and a direction. When I read this, I'm going to read this as each leg of my journey is its own separate vector. So I have one vector for my first leg of my journey and one vector for the second leg of my journey. So I'm just going to call those two vectors u and v. So my magnitude for u is going to be related to, well, here magnitude is going to be the length of my vector, right? We talked about that before. So how far is my boat going if I'm going 40 miles per hour for 2 miles? I'm sorry, for 2 hours? 80 miles, right? And above, we already converted the course into a standard position angle. So for our second vector, vector v, that was going 55 knots for 3 hours. So that's going to be 165 nautical miles. And my bearing there was 162. So starting at north and going clockwise. So that's 90 and then like 72 more. But we don't want a bearing, we want like our standard position angle. So that's going to be 90, 90, 90. That little section must be 18. So 288. So far, so good? Okay. Now that I have my vectors, or translated the information into vectors as magnitudes and directions, I'm going to convert these vectors into component form because it makes all the vector operations easier to do if I'm in component form. So to convert a vector into component form, we'll do the magnitude times cosine of the direction, comma, magnitude of the vector times sine of the direction. So in this problem, that would be 80 times cosine 235, comma, 80 times sine 235. And I'll just go to my calculator. So I have negative 45.9, comma, negative 65.5. Everybody feel okay there? I'll do the same formula now over here. So I have 150 or 165 cosine 288, comma 165 sine 288. So about 51.0. And then negative 156.9. Oops. 56. Any questions so far on what I've done? Now that I've written these into component form, it's a little bit easier to kind of see what's happening. So I'm going to draw myself a little picture. So I start off at the port, and I go 45.9 to the left, and then 65.5 down. So that's U. And then from the end of U, I'm going to go 51 over and negative 156.9 down. So like maybe down there or something. That's my V. And we're interested then in draw it. I'm using colors. This vector, which I'll call R. So if I think back to my operations of vectors, what am I doing to get R? When I line up my vectors head to tail like that, what we're doing is just vector addition. So that's what I'm going to do now to calculate R. Was 45.9, 65.5 plus 51.0, comma negative 156.9. Ay, ay, ay. Where did you go? So again, to add two vectors, I just add their x components and their y components. When I do that, I get 5.10, comma, negative 222.5. So far, so good. Okay. Now to find out how far the boat is from port, I just need to find the magnitude of R. And while I'm setting that up, I want to just point out to you, if we look at that component form that I wrote down, and I look at my picture here, does the 0.5 comma negative 222 look like about where I've drawn the end of our route? Definitely looks like it, right? Just a little tiny bit to the right of the port, but way, 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 way down. You guys see that? That's a good confirmation that you're doing the right stuff. So let's go ahead and finish computing that. So the guy, again, I'm going to use the whole decimals, so I'm just stealing it from my calculator output here. So I get about 222.5. And you might think for a minute that seems a little weird, but not really. I mean, if you think about it, most of the distance traveled is just down in the y direction, right? We've gone very little over to the right. Most of all of our movement is straight down. So if it's just basically the same as the y coordinate, that's just because the x is so small compared to the y. So far, so good? So that's one part, that's our magnitude. The other piece we need is to get the direction so we can find the bearing. So if I plot our point, or plot our vector, you know, that's basically this guy. And I want that angle, right? Well, if I go and I do the same thing that we did first semester, I need to find that angle. That's going to be my alpha between the terminal side and the x-axis. That part of the x-axis corresponds to 360 degrees. And I can see clearly that 360 is more than my angle, so I should do 360 minus alpha. And remember, to find alpha, we always do tan inverse absolute value of my y coordinate over my x coordinate. Just like we did in first semester. So when I do that, I get, oops. Okay, I am in degree mode. Oh, I'm so stupid. Look what I did. I did x over y. Gosh, Mr. Kulik. Try it again, dumbo. Yeah, I'll be perfect tomorrow. Today's now blown. All right, try it again. There we go. So 271.3. But what's the catch? In the problem, it asked for the bearing. Oh. So what do I have to still do? Yeah, I have to convert that standard position angle to a bearing, right? So I need that value now. So I'm going to do 90 plus alpha. Yes. Sure. Now, could I have just gone and done that immediately? Did I really need to find the direction if I was just going to need to find the bearing anyway? No. I guess you probably didn't. But I wanted to review just finding direction anyways, because that tends to be one of the more difficult skills. So I have 178.7. Okay. Now, again, that's a lot of stuff to do. But the individual steps themselves not bad, right? I'm just start by converting my information to a magnitude direction, take that, convert it in component form, add the two vectors, calculate the magnitude for that vector sum, and then the direction or bearing depending on what the question is asking for from that vector sum. So the individual steps, they are easy individual steps. They're things we've already done in homeworks. It's just putting it all together into a big process that, like, ugh, boy, that was a lot of stuff to do. It was. And after you do a couple, it'll be, you get comfortable with it. All right. The other application that we're going to look at requires a new vector operation that we're going to define here called a projection. So here's the idea. I'm going to start with kind of just giving you the graphical version of this because I think it's more helpful than anything else. So let's say we have some vector here, u. And I have some other vector here, we'll call that guy v. And what I want to do is I want to break up my vector u into some other vector that's in the direction of v plus some other, whatever the leftover stuff has to be that it's still equal to u. Now, we do this kind of thing all the time with numbers, right? If I say, I want you to write the number 5 as 4 and something else, well, it's really easy, right? 5 is 4 plus 1, right? That's all we're doing here is we're just breaking u up into a specific vector. The specific vector I want is the one that's in the same direction as v, and then whatever the leftovers is. So what this looks like graphically then is this vector we call the projection of u onto v. And this other vector I just called w, just from the alphabet. All right, because w, u, and v all, all go in a row. Is everybody okay with that? So this projection idea is really useful, especially in like the field of physics, when we talk about force application, right? If anybody has ever tried pushing, like if your car's stalled and you put it into neutral and you try to push your car, what do you end up having to do? You need to like lean into the car to really get it to move. If you try to stand straight up and push it, you're not gonna have a whole lot of luck, right? You have to like get down and like get your angle similar to the direction you want to be pushing. So more of your force is applied in the direction of the car. Ideally, you'd like to be able to lay on the ground and push completely horizontal, but like our legs don't work that way. Does everybody feel like you kind of understand what I'm saying? Okay. So to actually do this calculation of how I do this vector or this projection calculation, let me write that down on how we actually do that calculation. So given non-zero vectors u and v, the projection of u onto v is u dot v over the magnitude of v squared times the vector v. Now remember, the result of a dot product of two vectors is just a number, right? The magnitude of a vector is just a number. So what we're talking about here is just a scalar multiplication, right? Just wanting to point that out to you. Now, when I drew this picture up here of kind of what was going on, notice how long I drew V, right? But in all reality, all I need from V is really the direction that it's going. So in a lot of these story problems, we might not give you enough information to know the magnitude of V. In those cases where you're not given enough information to know the magnitude of V, like there's no indication of length, we're just going to assume that V has a specific length. What length would be the easiest to assume? 1. We want to assume that V is a unit vector. Okay? So that'll come up in some of the story problems here, the examples that we'll look at. But we're not quite ready to get there yet. I'm just going to dump in those couple of notes that we just mentioned, that really all this formula for projection is like a fancy scalar multiplication, and that in a lot of cases the magnitude of V might not even really matter. In those cases we're just going to assume it to be 1 because it makes all the calculation a little bit easier. Everybody's okay? That's all those words there are saying, just the things I explained very briefly. All right, let's practice doing this projection calculation before we get to a story problem. So our example says, find the projection of vector u onto V, and then after that, express the vector u as the sum of two orthogonal vectors, one of which is the projection. Well, that's fine, right? Like when we did this before, or when we drew the picture, there was a right angle here, so all we're really looking for is to write u this way. So to start though, let's just start by finding that projection. So the vector we're projecting onto is the subscript, and the vector doing the projection is the argument. So if I just kind of copy the formula in, that's my formula. And I'm going to just substitute in the values for u and v as my very first step. Yes, sir. Sure thing. So far, so good. Haven't really done anything other than plug numbers into my formula, right? To do a scalar multiplication, we start by doing the product of the x components plus the product of the y components. To do the magnitude, we have the square root of the x component squared plus the y component squared. And then we have that extra squared there. Is everybody okay with what I've done so far? All right. 6 times 3 is 18. 1 times -4 is -4. So I have 14 there. 6 squared is 36. -4 squared is 16. So that's over the square root of 52. Oops. Before I do that, I notice that the squared and the square root are just going to cancel, right? Just do that now. So I just have 14 over 52. So far, so good. I notice 14 over 52 can reduce to just 7 over 26. Then I'll do my scalar multiplication. And again, I notice that I can reduce each one of those parts. So I get that the projection vector is 21 over 13 comma -14 over 13. Does that feel okay so far? Now the arithmetic was kind of stinky there, but like, again, it's just combinations of these sub-skills that we looked at in sections 1 and 2 should be okay with, like doing a magnitude, doing a dot product, and then it's just like arithmetic along the way. It was kind of gross arithmetic, but like, you know, we can handle multiplying fractions together. We may not like it, but we can do it. All right. So that's the first part of the problem. It then wants us to break u up into the sum of these two orthogonal vectors, right? So I know that u was the vector 3, 1. The projection vector we know, we just found that. And we still need to find w, right? What do I need to do to both sides of this equation to find w? I'm just going to subtract the projection vector from both sides, right? Just like algebra 1. Just we're doing the same concept, but instead of a number, we have a whole vector. But like, what did he do? Conceptually, it's the same thing. Okay, to subtract these two vectors, I just subtract the x components and the y components. But to subtract the components, I'm going to need a common denominator. So 3, I'm going to just think about as 13 over 3, and 1 as 13 over 1. So I have 39 over 13 minus 21 over 13, comma 13 over 13 minus a negative 14 over 13. So I get then 18 over 13, comma 17 over 13. That's my w. So I can say my u, which is 3, 1, is equal to my projection vector plus my w vector. Oops, 17, Mr. Kulik, come on now. 27, don't forget to carry the 1. Ah! Somebody would have caught me there, I'm sure. So that's how I rewrite u as the sum of two orthogonal vectors, one of which is in the same direction of v, that being the projection vector. Is that okay? Okay. So let's look at, we'll do a couple of example problems now of like a real life situation, aka a story problem, where we can use this projection or where we have to use this projection calculation. Oh my goodness, come on now. Fine, whatever. Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? So we're looking for, in this problem, we have to identify some vector that represents the force and project that onto another vector representing the hill. That's the idea. Okay? So if you're sitting at the top of the hill, what force causes you to slide down? Gravity. So we're going to have, that's our force. We're going to have gravity. That will represent that with a vector. And then our other vector is going to be for the hill. I'll use G and H then to help me keep everything straight. So I remember like which one is gravity, which one is the hill. All right. So in this problem, what is the magnitude for gravity? For the force of gravity, what is the magnitude there? It is the 165 pounds. Remember, gravity is what gives objects weight. Because if you take the same thing up into space, it floats around and there doesn't have any weight anymore because gravity is, you've escaped the Earth's gravity and you're, unless you start spinning artificially and create your own gravity there. Everybody's okay there? Now, what direction does gravity pull us? Always straight down, right? So our gravity vector looks like this. Everybody agree? So what is the direction then for that gravity vector gotta be? 270. Very good. And as long as we're at this, let's convert that gravity vector into a component form. So again, we'll do magnitude times cosine of the direction, comma magnitude times sine of the direction. And when we do that, we get 0, comma negative 165. You might have been able to look at the drawing that we drew of gravity and go, oh, the component form certainly has to be 0, negative 165 if it's going straight down. Its length is 165, so it's 165 straight down. I didn't want to start by doing that because, well, you can't do that every single time. I mean, gravity does that every single time, but so far so good. All right. Now let's look at the hill. Are we given any information about the length of the hill, which would correspond to the magnitude of our hill vector? Do we know how long the hill is? Anything about the dimensions of the hill? That's going to be a direction, right? Because it's in a degree. What do we do if we don't know anything about the magnitude of the vector? Set it to 1. So this is, we're just going to make that assumption. Assume that the magnitude of h is 1. Now if I draw my hill vector, my sled's kind of doing this, going downhill, right? Everybody agree with that? And it tells us the angle of incline is 25 degrees. So like that's a 25-degree angle, right? Everybody agree? That's what. So from geometry, I remember that alternate interior angles are congruent. So my hill direction is going to be 360 minus that 25 degrees. Everybody feel okay there? Or that's going to just say that 335. So just like before, I'll resolve that to component form. Where's that? There you are. So I have cosine 335. And then sine 335. So I have 0.91 comma 0.42. Meant negative 0.42, excuse me. Everybody so far so good? All right. The question again asks what amount of force is sliding down the hill? So that amount of force is going to be the magnitude of that gravity projected down the hill. So it's going to be the magnitude of that projection vector. Okay. So a helpful little theorem here for us that we can use is if I do the magnitude of a scalar times a vector, that's going to equal the absolute value of the scalar times the magnitude of the vector. Why am I pointing this out to you guys? Because if I remember my vector projection formula, I have scalar multiplication there. So rather than having to do all the arithmetic, this makes life typically a little bit simpler. All right, so let's go ahead and start filling things in. So I have the dot product of G and H over the magnitude of H. And remember, the magnitude of H is just 1, right? We set it to be 1. Oh, nice. And the magnitude, and then we have times the magnitude of vector H. I'm going to put in one extra step here just for if you're following along. later, so it's a little bit more connected to what we just did. So I'm going to add that extra little step there where I use that little theorem that I wrote in symbolically. And now I'm going to fill in the numbers. That's probably a little bit more straightforward, right? That's pretty rad, though, that I didn't actually have to compute the magnitude of h. In fact, I don't actually have to do a magnitude calculation anywhere in here. Since all those magnitudes are just 1, I don't have to do the scalar multiplication, then do the magnitude. Ooh, what a nice little shortcut. Thanks, helpful theorem. So really my force is just going to be the absolute value of this dot product, right? That's pretty rad. That works out that same way. Anytime you're projecting onto a unit vector, we can just do the absolute value of the dot product. So my answer should be 79 or 69.7. That's pretty cool. I have one more example to get through, and then we'll be done. You guys had a lot of questions for me, which is great. That means we have to scoot a little bit here at the end. All right. This one, a little bit different. It says a crate is being pulled up a ramp at an angle of elevation of 40 degrees. With a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assume that the crate is of negligible weight. What is the amount of force directed up the ramp? Now notice here, there is no gravity vector in this problem. What in the story problem tells me that there is no gravity vector? Nope. The crate has no weight. Can gravity act on it? Is gravity acting on it? No, man. Now, if the crate did have a weight, we actually would have 3 vectors going on. We'd have 2 force vectors, the force of gravity and the force of the pull, that we'd have to project onto the ramp. So you just take the 2 vectors, add them together, and then do the projection. If you have more than one force vector, you just add them up and then project onto whatever surface you need to project onto. No big deal. Here there's not, but I think in the homework that happens where you might have 1 or 2 vectors going on that you have to project. You just add them first and then do the projection. No big deal. All right, so our only force vector is the pull. And then our other, we're going to be projecting that onto the ramp, right? So the magnitude of that pull vector is the 100 pounds. And the direction, if I think about what's happening here, we're pulling up. So like our force vector looks like this, right? So our direction is just 40 degrees. Oh, I like it when that happens. That's nice. So I'll convert this into component form. And into my calculator you go. So 76.6 and 64.3. Okay. Our ramp vector, well, here it says the ramp goes 2 feet horizontally and, 10 feet horizontally and 2 feet vertically. That's dimensions for the ramp, right? So if I think about what that means, the ramp is kind of going 10 feet over and 2 feet up, right? Well, that's just telling me the component form for the ramp, isn't it? Oh, I like that. Boy, that's simple. I don't even have to translate anything. It just, boom, there's my component form. Yes. All right. So now what I need then is the projection of the pole onto the ramp, or the magnitude of that projection. So that's the magnitude of P dot R over the magnitude of R squared times vector P. But I know I can separate that into the absolute value of the scalar times the magnitude of the vector. So I'll do my dot product. So I have 10 times 76.6 plus 2 times 64.3 over the square root of 10 squared plus 2 squared, all squared. But I remember here the square root and the square just cancel each other out. And the magnitude of P, well, hey, that's, yes, sir. Oh, my goodness. It is. Yeep. Thanks there. I was doing the magnitude of R. I definitely didn't write the magnitude of R. Whoopsie daisies. Okay. So, to do that dot product, I have 10 times 76.6 plus 2 times 64.7 or 3 or whatever. So I have 894.6 over 104 times the square root of 104. And we'll just do it, right? So 87.72. So that's one where there was no shortcut, but even when there wasn't, like, it's really not that bad, right? This shortcut helps enormously without having to muck around through the scalar multiplication and then do another magnitude. It's a nice little time saver here. So to add to PS2, we're going to assign problems 41 through 50. That's the new stuff I've just added to PS2. Remember, last week we already assigned 15 to 40. Both of these together are going to go into PS2 due at Sunday at midnight. So again, typically I just kind of keep adding assignments in as the week goes on. As a heads up, what should we expect to see this week? Homework quiz covering 8.1 and 8.2. Yep, so just converting between the different vector forms and doing the vector operations.
Could you scroll up a little bit more? Thanks.
Is that far enough?
Yeah.
Okay. We'll do a delta math assignment this week to just practice some of these basic operations, these 8.1 and 8.2 things. And we'll finish up chapter 8 with section 4. We're not doing sections 5, 6, or 7. They're all the 3D stuff that's beyond the scope of what we need to be covering in this class. So section 4 will be the last section in chapter 8. So we can expect to probably do the chapter 8 test the second class day next week. We'll have a review day, and then the test will be the second class day next week. Again, at least for Ethan's sake, for every test, you're allowed to make like a half sheet of notes. They're due before the test day to turn in, but you can put anything you want, front or back, whole thing. If you want to start working on it now, you're welcome to do that, or you can do it on the review day. It's basically a free period to kind of work on whatever you need to that day. But just giving you a heads up that that's something we do. If you want to think about it in advance, you're welcome to. A lot of people don't.
Are we gonna add anything? Are we gonna learn anything more?
We do have one more section to cover, yep. And it's one where highly recommend you save a good chunk of space for that section, because well, there's like a kind of a decision tree thing that we're going to build that would be I think would be nice to have, and a couple of like calculation samples that's like, okay, that's how you check for that, that's how you check for that, that's how you check for that, in order to kind of sift through the decision tree that we'll build for that section. But that's the idea. At least that's tentative in my head. Obviously, like, snow days can throw the monkey wrench in that, or if, like, you know, a day goes really poorly and it's like, ooh, boy, we need some more time. Like, I'm not opposed to adding another day here or there if we just need some more time to do stuff, you know, that's okay. But that's tentative. Like, everything is based on how you guys are doing or how we're feeling, right? We're in good shape, though. We got a lot done first semester, so no big deal.